Hi, this is lecture 18, ET250, and we're going to talk about ideal transformers and its dot convention, just a continuation from the last lecture. We're going to look at the sign implications, compare it to a gear, and then see how the mutual inductive or inductance equations match the ideal when k equals 1. We'll also look at how to set up the dots, go through a full example, and then expose what are some common markings and then practical concerns. Okay, so let's begin. So ideal transformer. Well, when we had this from last lecture, we have V1, V2, I1, and I2. And if you recall, we had V2 equals plus or minus N2 over N1 V1, and I2 equals plus or minus N1 over N2 I1. Okay, notice the ratios are flipped, and I always have the 2 or the output on the left. Okay? And as we said before, that dot convention determines sign. And if you recall that if you have a dot on the primary side, if you increase, right, either by increasing the voltage or sending current in, you're going to increase charge on the other side. So if you increase charge on the input, you're going to increase charge on the output where the other dot is. And that's either going to send current out or you're going to have voltage build up on the side. Okay? And so if we look at the voltage, imagine if we have a voltage source here at V1 and we're increasing the voltage here. Well, we're going to build up a charge at this dot. And if we happen to be reading V2 in this configuration with, for example, this multimeter, red lead here, black lead here, we're going to see a positive number. Okay, V2 will be positive. And so in this case, we would have a positive here. Now, what about the current? If we have I1 entering here, we're going to build up a positive charge on here. Now, if we define some current here and we connect this to another circuit, what's going to happen is we're going to get I2 flowing out of this dot. And so again, this is going to have also a positive on that. And so note in this positive, right, we're going to have both V positives touching. And note here for this positive configuration of current, we're going to have I1 entering and I2 leaving. So one of the currents has to enter, one of the currents has to leave. So if we were to summarize that in a set of rules, we could say that, well, if V1 and V2 have the same polarity with respect to their dots, use the positive. Otherwise, use the negative for here. And for this one, if one current enters and the other leaves their dot, use a positive. Otherwise, use a negative. Okay, so let's just do a bunch of examples and see if we can just hit this concept home. So if we look at the voltage, positive, positive touch, that's going to be positive. But the current, look, both are entering, so that means it's going to be negative. Good. Okay, let's look at the next one. Here we have a positive, negative for the voltage, so that's going to be a negative. And let's double check. Yep, negative. And here we have current entering, it's dot, but then this current I1 is leaving, so that's positive. Good. Okay, let's go look at the next one. For here, we have V1 positive touching V2 negative, that's negative. And we have I1 entering and I2 technically entering, so that's negative. Good. And let's look at this last one here. If we have V1 and 2 both positive touching, that's positive, great. And we have I1, what is it doing? I1 is entering, in fact, and I2 is leaving, that's also positive. Excellent. Okay, so not too bad. Pretty easy to use the dot convention to determine the sign. Okay, so what does the positive and negative even imply? Like, what does it mean? Well, let's say we have a positive version, V2 equals positive N2 over N1 V1. And if we were to graph both on the oscilloscope, what we would see is maybe something like this, where V1 is like this and V2 is some scaled version of N2 over N1 like this. But what we notice is they would be in phase. V1 and V2 are in phase if we have a positive. Now let's say we had a negative version right here. Okay, well, V1 would look like this, but V2 would be the opposite, and they would be completely out of phase. So that's what the implications of a positive or negative. Now, it's important to get this right, especially if you're paralleling transformers or if you're connecting things to it. If you don't have this positive and negative phase correct, you can blow things up, right? Because you could be sending a positive current when it should be a negative and vice versa. Okay. Now, the next question might be, how would you remember if it's N2 over N1 or N1 over N2? It's always easy to get those confused, right? And so one way to do it, if you had a little time, is to go back to our hydro analogies. Well, we know voltage is the same as pressure, or the analogy is pressure, which is kind of like a force or a torque in a rotary system. The current is a flow, current flow, right? Which is like a velocity or an angular velocity if it's a rotary system. And so what I like to do is think of gears, because a transformer, an electrical transformer, is like a mechanical transmission or gear set. So let's look at this situation. We have torque 1 and speed 1, omega 1, and N1, and N2, and torque 2, and omega 2, where N is the number of teeth as opposed to the number of turns in a transformer. Okay, so by inspection, what do we note? N1 is definitely smaller than N2, and we definitely note that in this situation, that this omega would probably spin faster than omega 2, right? So we have N2 bigger than N1, and we have omega 1 bigger than omega 2, right? This is going to spin faster. We all have a sense of that, right? As unlike transformers, where it's like, we don't quite have the intuition yet. So you could easily write this equation, omega 2 equals N1 over N2 omega 1, right? The omega 2 is definitely going to be the smaller one of this, so we're going to put the small N1 here because we know the small N1. So that would immediately help you write this with this relationship. And we all know that if you memorize one, you memorize the other, right? So the torque is just the inverse, right? N2 over N1. Now, if you go back to the hydro analogy, you know that current is like this velocity, right? So that just replace omegas with I's and torques with voltages, and you would get our our transformer equations, right? I2 equals N1 over N2 I1, bang. And V2 equals N2 over N1 V1, bang. Nice. So just a way to think about it and relate it to the mechanical gear analogy, and also remember if it's N2 over N1 or N1 over N2. I hope that helps. Okay. Now, another question might be, do the mutual inductance equations and the ideal transformer equations actually match when K equals 1? Well, they do, and let's convince ourselves that this is true. So let's draw a little transformer system. We have our dots, and if we look on the left, what do we have? The I1 goes into V1, that's a positive passive sign, and I2 leaves V2, so that's a negative passive sign. Okay, that's good. Okay, now what about using the dot convention for the sign? So I2 is leaving its dot, and V1 positive is touching its dot. That's a negative. Okay, so that's this one. Good. And then what about I1 and V2? I1's entering its dot, V2 positive touching its dot. That's a positive. Great. Okay, we just did this for the ideal transformer, right? V1, V2 positive touching, that's positive, and I1 entering, I2 leaving, that's positive. So what we should see is if K equals 1, these better match. So we better be able to start with this general version, substitute K equals 1, and get these ideal transformer equations, right? And so recall the mutual inductance, this M guy from the last lecture, is K L1 N2 over N1 or K L2 N1 over N2. And we showed ourselves that that was true. And we also remember if we divided the inductances, it's the same as dividing the square of the turns ratio. Okay, and that's from the previous lecture. Well, what we could do is we can go here and start with this equation, and notice I substitute the L1 version for M here and the L2 version for M over there. And the strategy would be, well, I have V2 here and I want this V2. Could I solve for this guy and then plug it into there so I get something in V1? Maybe these DI2s would cancel. Well, let's do it. So this guy here, DI1 dt, I could solve for this whole term by just bringing this over. So look at this, V1 plus this whole term, KL1 N2 over N1 DI2 dt. Good. And then I can just divide by L1. That's pretty easy. Look, the L1s cancel and I get 1 over L1, no problem. And then I'm going to just take this and put it in here. So what does this become? V2 equals this guy minus L2 DI2 dt plus this guy here, KL2 N1 over N2 times this guy here. Okay, not too bad. Now, if we look closely, what happens? I get a K squared, I get an L2, and oh, nice, these cancel out. I also get a K, an L2 over L1, and an N1 over N2 V1. Great. And if I look even more closely, look how this L2 and this L2 negative are going to cancel if k equals 1. Yay. And if I look over here, remember that n2 squared over n1 squared is the ratio of L2 over L1. Can you see that L2 squared is going to cancel, one of the 2's is going to cancel with the n2, and one of the squares is going to cancel with that n1. And if k equals 1, I am left with v2 equals n2 over n1 v1. Fantastic. They do match if k equals 1. Pretty cool. What about the current though? Well, if it's ideal, what is conserved? Power. Power is conserved. So that means that the power of this side plus the power of that side equals 0. So what's the power of this side? I1 V1, positive. What about this one? This is I1 or I2 V2, but negative because the current's leaving the positive terminal. And so we know P1 plus P2 equals 0 by the conservation of power, which means this equals this. This minus I2 V2 equals 0. Well, I can solve for I2, right? So I can bring it over, and I know that I2 is equal to V1 divided by V2, I1. Well, we already have that ratio right here. And so I get I2 equals N1 over N2 I1. Yes, that is fantastic. We are seeing a consistency in our result, okay? So they're the same thing, except that this is a special case of the general version, all right? So then maybe the question is, well, how would you set up the dots in the first place? Well, remember the dots tell us the relative windings of the coil. So unless you can see the windings, you don't know how to set up the dots. So we need to see how the coils are wrapped. And so the way that it works is if you have a test current, and if the test current were to enter their respective dots, the flux due to Ampere's law, right-hand rule, would flow in the same direction. Okay, so let me illustrate that by an example. So let's look at here. Let's say we have a transformer, right? And so we have a coil here and a coil here. Now notice, if I have a dot and I have a test current and I use my Ampere's law right-hand rule, which is this guy, right? Ampere's law right-hand rule. Can you see how the flux 1 would go up? And over here, look at this. I have a dot here and I have a test current going in, which means I'm going to have my flux 2 going down. But can you see in this transformer, flux 1 and flux 2 are in the same direction? So in this specific transformer, you'd have a dot here and a dot here, and that would satisfy the dot convention. Pretty easy to set up. Okay, what about over here? What about this kind of weird situation where this is also considered transformer? Well, let's check it. If I have a test current entering this dot in this coil, can you see how flux 1 is going to go up? Okay, good. Use the right-hand rule. What about this one? That means I want flux 2 to go up. Good. And that would mean a dot would have to go here on the bottom, okay, to get this test current to go in here. Okay. Okay, good. So what's the process? The process is pick a terminal, any terminal on any side, and then add a dot. And then check the flux direction. Okay, and then choose the dot on the other side to match the flux direction. Pretty easy. 3 steps, no problem. Okay. So let's go and do an example. So let's say we had this example here where we had a transformer coil. We have I1, V1, I2, V2. Now we don't have any dots in here, but we want to set it up. So what do we have here? We can pick a dot on any corner. We can write the mutual inductance equation, write the ideal transformer equation. So let's say this is our full example. Let's do it. Okay, so let's pick a dot. So if we pick a dot, could have been anywhere, and we can check the flux, right? So if this goes in like this, right, it's coming in and going around, that means the flux is going, by the right-hand rule, going down. You can see it, phi1. Now on this side here, we can see, well, if I want the flux to keep going the same direction, I would need to pick a dot over here to get the flux to go up, but in the same direction as phi1, phi2. Fantastic. Notice though, be very careful. Notice, did I have V1 and I1 or V2 and I2 in the picture when I set up the dots? No, I did not have these currents and voltages in here. I had these test currents, sure, but they were independent of these V1, V2, I1, I2. Okay, well now let's write our mutual inductance equation. So can you see how this transformer with all the coils and its full glory is equivalent to this diagram now? Here, what's nice about this, you don't care about the individual wrappings. The dots give you all the information you need, okay? So now I have V1, I1, V2, I2, all its labels, the proper dots, diagonal dots. I'm happy. And now I can go and proceed and write the mutual inductance equations and the ideal transformer equations. So let's do it. So for the mutual inductance equations, what do we have? I1 leaves the positive terminal, so that's going to be a negative for the self-inductance. Good. And what about here? I have I2 enter the negative terminal, also negative. Good. Okay, well, what about the mutual inductance term for the V1? I2 enters its dot and V1 positive touches, so that's positive. Well, what about here? I1 leaves its dot, but V2 negative touches, so that's positive. Excellent. So this is the mutual inductance equations. And what about the ideal? Well, V1 and V2 have a positive negative, so that'll be actually negative. Good. And what about I1 and I2? I1 leaves and I2 enters. That's positive. Great. And so this would be a full example where you're given a transformer, you're given the labels and current directions, polarities, you set up the dots, and you wrote the mutual inductance and ideal transformer equations. Pretty nice. Okay, the last two things I wanted to go over are some common markings for a single phase transformer. So typically you'll have a high side and a low side voltage, and they denote those as H's and X's, okay? And the dot convention actually determines where you put the H1 and X1 terminals. So for example, if you had the dots like this, you'd have, and let's say the left side was the high side, you'd have H1, H2 where the 1 is connected to the dot, and X1 where that 1 is connected to the dot. If you had it like this, you'd have H1 here and X1 there. Pretty simple. Now, what they call this version, this diagonal, is called an additive, and we'll see that in a later lecture or maybe in a following class. And this is called a subtractive, right? So this is actually a better way to do things. This actually is used for high, what we call kVA transformers, like greater than 200 kVA or 8,660 volts. That's just a spec, right? And there's going to be less voltage stress, right? By the way, I know you haven't heard of the term kVA yet. It's the units for apparent power. We'll be discussing this later, right? A lot of legacy transformers use this additive approach, but this is actually the better way. This is the subtractive approach, okay? All right. The last thing I wanted to talk about is some practical transformer concerns. And what are they? Always use transformers as designed. Now we know that you can technically, theoretically, that you could have a step up or a step down, just kind of switch what you consider the primary. But you always want to keep the primary and secondary as designed. You don't want to be switching them even if this works in theory. Okay, so always use it as designed. Don't exceed the voltage ratings, right? So if you have a 10-to-1, you also have to know, well, what's the input primary maximum voltage? So just because you have 100 volts and it goes 10-to-1, 1,000 volts, right? That might be okay, but then if you double the voltage on the input, and which doubles the voltage on the output, you might destroy some insulation. So don't exceed the voltage ratings. Also, don't apply significant DC current. There's a certain amount of impedance, which is AC resistance, that is supported by these transformers. If you will supply the DC current or a significant amount, the problem is it'll allow a lot of current to flow, and that would be bad. That could be bad, again, damaging the transformer. Okay, and then the last thing is only apply a specified frequency of voltage, right? If you supply it with too low or too high a frequency, again, you could damage the transformer. So just make sure whenever using transformers, read the spec and use it as designed. Okay, I might have a follow-up lecture to this to talk about what I talked about last lecture in that weird simulation. But for now, this is I hope this is helpful, and I hope you learned a few things. All right, see you in class.